So, last time on mechanics of materials, um, we were messing with pressure vessels, namely thin wall pressure vessels. Can I just call? Can you tell me some of the assumptions that went into that analysis? Say say again. Okay, so we're more or less ignoring the ends. Since yeah, whether they're rounded or not, we don't really care right now because we're going to ignore them because ends make everything change in very unpredictable ways. So we're not messing with the ends right now. What else do we have? Namely, just like the thin wall part. What made them thin? Right. If you look at like a ratio of thickness, or radius to thickness, it should be greater than 10. The radius should be more than 10 times the thickness of the wall. All right. What else? What else do we got?
No bending.
No bending. Right. No bending. They're not really. That's not really a design case. In a sense, it's an off design case. That's what happens when crap goes wrong. So things are already broken by the time that it started to bend. So no bending. What else?
Stress distribution is about average stress.
Okay, yeah. So we're saying we're going to say that the wall is so thin. If you can imagine, this is like the wall of the pressure vessel, some thickness T. We're saying that the wall is so thin that distributions of like shear stress we talked about last time, because we're saying that there's no bending. The distribution of shear stress is so small that we can effectively ignore it, as well as that if I have some normal stress, so like if I have a bunch of force coming out of the page here, that it's not that which called it's not really that that the distribution is more or less the average in stress, so just a force over area kind of thing. So yep, it's another one. What else we got? We need to worry about variations in stress, depending on, like if we're looking at the top, bottom, left, or right. Why? Right, we're making the assumption that this is filled with some gas, some pressurized as gas that's pressing out uniformly on all sides. So, and that the tank itself, the geometry is axisymmetric. So no matter how I rotate this guy around, say like a long axis here, no matter how I rotate that, the geometry is always going to look the same. So what you call it, it's axisymmetric. We have a uniform pressure distribution. We're ignoring end effects. We're ignoring the ends completely. We're saying we're not caring about bending. Bending happens after something else has already failed. We're ignoring shear stress for now. We're saying that the walls are so thin, and less than a tenth of the radius. This is that the average stress is the actual stress that's in the wall, and pressure and stress distributions don't really matter. All right, we cool with those assumptions? All right, uptake sounds for the most part as sent. Either that or which email starts speaking for everyone. All right, so assumptions, woo, assumptions. More assumptions. Okay, and that got us up to here, where we start talking about the different kinds of stress that are there. Because based on our assumptions, we're saying that there's only normal stress, essentially. And if we look at our tank, Hank, you said that there are a couple ways you can get that normal stress. One is that if I have this tank here, it can choose to, say, like blow apart in that direction or like in that direction, right? So it can burst laterally or vertically, or because we're axisymmetric, you might say burst apart in the radial direction, okay? And that gave us what a bunch what a bunch of people call hoop stress. So if I take my tank, I section it down the middle, and so I'm looking at section of the tank. Oops, need to draw some thickness here. Okay, so this has some radius, has some thickness, and there's some gas in here, right? And this gas is pressurized, so there's some pressure distribution here, uniform pressure distribution, because we made that as assumption. And by the same token, because this is a section, we know that this material is also transmitting some force, right? There's some like reaction force there. So we went through the math last time and said, okay, pressure is what? A force over an area? So if pressure is force over area, that means that I can get the force that's pushing this way by just pressure times whatever this area is. Or if I looked at this if I looked at this in a different view, make these colors consistent somewhat. This is the gas, and this is the material. Cool. That'd be like the area that the pressure is acting on. Call it like, I don't know, AP. And these two combined would be like the area that's reacting that pressure force. So if we crunched all the numbers from that, we got said something like that is an expression for the hoop stress. This was in part we made the assumption that that's the next one that would make that assumption. Yeah. Which is fantastically straightforward and easy. Great. And then we said, okay, so it can burst apart radially. That's that part, but it can also go apart longitudinally, right? So two ways is that vessel could break. So if we work up an expression for that, we can follow kind of the same logic. If you're looking down the barrel of the vessel, looks something like this. That's all pressurized fluid. That's all material. Cool. Or if you look at it from the side, you have some sort of so you'd have your uniform pressure distribution here pressing in, and then you'd have a kind of like circumferential. I'm not drawing all of the arrows, because they really go all the way around. You have some ring of internal forces is reacting to that, right? So I said, heck, can do the same kind of thing. Pressure is force over area. We find the area of that. Because it's a thin wall pressure vessel, we can compute the area of this outer ring in a more simplified fashion, instead of doing like pi r squared of the outer radius minus pi r squared of the inner radius. Instead of doing that, we can say, heck, this is, if I draw a line around the middle of this ring, so at some distance like r plus the thickness over 2 from its center, that if I kind of like unwind that ring, like say I have this, and I unwind it, and I say that line has some thickness, right? It's kind of like if I take that thick ring and unwind it here, then it's kind of like just a big rectangle, right? So like it's like the thickness of that times its times its length, or the circumference of that circle, would be like the area of that circle. At least it's an approximation of it. That for thin wall pressure vessels is good to at least 5% of the actual area, and it simplifies our math. So we're going to use it. So instead that like the area of this, something like that. Well, and if you wanted to, you could replace r with hang on, get some more room. And if you wanted to, you could replace r by the r plus t over 2. And at least for this first option here, if you do that and you crunch the numbers, you get something like that for the longitudinal stress developed in the vessel. Yes. In the bottom one? Yes. Yeah. Note that the longitudinal stress equation is derived from the top one, although you could figure it out from the bottom one too, if you wanted to. All right. So that's kind of where we left off. So the question is, now that you know the longitudinal stress and the hoop stress at any point, we know there's no shear stress, at least on the inside of the vessel. So like if I had an element like right here, there's no out of plane stress. There's no sigma z. So how do we make more circle based on that and try to find a failure criterion for this vessel? That's kind of the open question. So let's have a look. Okay. So do I want to go back there? Yeah, let's do that. All right. So Moore's circle. Each circle here corresponds to a different pair of points on the sigma axis. And what do we call those points where Moore's circle intersects the sigma axis? Principal stresses, right? Or the normal stresses acting on a particular section where there's no shear stress. So you can label them like sigma 1, sigma 2, and sigma 3. So there are 3 principal stresses, right? Because you have 3 coordinate directions. And that's essentially how you build a generalized Moore's circle. You try to identify what these 3 things are. Now, if you have all of your shear components and all of your normal stress components, that becomes really, really freaking hard. You actually have a cubic equation that you have to solve, which isn't fun, and it's difficult, if not impossible, to do analytically. So we're not going to look at that. Instead, we're going to look at it via plane stress. So we're ignoring a bunch of these components and actually becomes something that you can solve. So in the case of the thin wall pressure vessel, do we have any shear stress? Or are we assuming that we have any shear stress? Say again? Right, there is no shear stress. So we have our hoop stress, we have our longitudinal stress. If I looked on an element that would be wholly in one plane, right? Because we also said that our out of plane stress is 0. So what are our principal stresses for this case? At least two of them. Right, because this exists on a section where all our shear stresses are 0, which is the definition of a principal stress, right? So that means that these 2 points here, say, I'm just kind of picking points, would correspond to hoop stress and longitudinal stress. Just kind of plot them, and then the third principal stress would be 0, because that's what our other normal stress is. So let's kind of draw this out. So if I bop over here, and let's say we have a tank, some kind, has some radius, has pressure, say 180 psi. Radius is, where are you? (15 inches). Wall thickness is 5/16 inch. Really? Come on. Come on, work with me here, board. Thank you. Okay. Wall thickness is 5/16 of an inch. The expression for hoop stress was, so he says,
PR over T.
PR over T. Okay. And longitudinal stress was, okay. And we're looking at the inside wall. Remember I said that it's on the inside wall that sigma z is 0. So what would the radius of interest be? Or sorry, yeah, I guess I didn't define in this as well. If the radius is a radius to the outside of the vessel, you have to take off the thickness in order to get to the inner wall, right? So like if this radius goes to the outside. Called the radius that you care about would be like r minus t, right? So just something to keep. Just something to keep in mind. So let's say that this is. You can do you can do that, but you need but you need to read derive these in order to use that. Because remember I said this is derived for the inner radius. It's not derived for the r plus t over 2 thing. Yeah. So we're just doing the inner radius now. You can if you want, but that's what these equations are solved for. So if we assume that, rather, if we say that that radius is to the outside of the wall, we can work these equations. Say, okay, 180 psi times 15 inches minus 5/16 of an inch divided by wall thickness, and that gets us a stress that looks like what? Go calculators. And if someone could crunch out the numbers for what's called for longitudinal stress at the same time, that'd be awesome. For what? And what units? PSI. Cool. 8,460? Cool. Okay, and for longitudinal stress? Actually, I guess it's just half that. Cool. All right. So we have some stresses. We know that because we're on the inner, the inside wall of the cylinder, that sigma z is 0. We know that all our shear components are 0. So these are our two principal stresses. We can say, okay, there, say that's about 4,230. That would be about 8,460. So 8,460 psi. Just put a sigma L there. Cool. We can find the center of that circle, right? Be like a sigma average kind of thing. So whatever the average of that is, call it there. It's like what, 6,345 or something like that. And then and then the radius is also you can get via the same kind of logic, right? So we can draw our first circle here. Alternatively, if you don't want to run the equation for radius, the square, which is called the root of the quantity sigma x minus sigma y over 2 quantity squared thing. You can also just say geometry is awesome, and subtract to find the difference between the center and one of the principal stresses. Up to you in this case, because it's all nice and defined for you. Okay, so that's kind of like our sigma 1, sigma 2 circle, because those are the principal stresses included in that particular circle. What's our third principal stress, since we're on the inside of the pressure vessel, since we're on the inside wall of the pressure vessel? Say again? Right. Our third principal stress, which would be the out of plane principal stress, would be 0, because this is our set of principal planes. This is where shear stress is 0, and the out of plane stress is 0. So that means that our third principal stress has to be right there. All right? So like if I wanted to label principal stresses, I could go like that from greatest to least. And because that one's there, and I know, and I can say, well, if this is my sigma 1, sigma 2 circle, I also have a sigma 2, sigma 3 circle. There's circles connecting to all different principal stresses. So I know if I know the 2 points where the sigma 2, sigma 3 circle intersect the sigma axis, that means that I can figure out where the middle of it is, what the radius is, and all that, because I know that which is called the circle sits on the center of the circle sits on this axis. So just the average of sigma 2 and sigma 3 give me that center point. Are we happy with that? I can do the same kind of geometric trick to find the radius and all that jazz. Now how do I draw the last circle? This is sigma 1, sigma 3 circle. Right. It's just connecting the last 2 dots, sigma 1 and sigma 3. So I just do the same tricks. Average sigma 1 and sigma 3. I get the center point, find the radius, draw my circle, and go, oh crap, I have a really, really large maximum shear stress. And that shear stress would be what? Well, what geometric quantity would it be equivalent to? Say again, Stressel, and you said something too? Yes, okay. So, in this case, the rate which call whole, you're both right, because the radius should be equivalent to sigma L, because your third principal stress is 0. In a more robust sense, it's always your radius, though, the radius of that third circle, which you can find by whatever geometric mean floats your boat. All right, and that in turn, according to the failure criterion that we've been going with, gives you the maximum shear stress experienced by an element on the pressure vessel, which you can then compare to your yield stress and get whether or not the thing's going to fail. All right, that's pretty much the generalized Moore's circle. If you wanted, now that said, if you wanted to find stresses along different planes, I mean, it's all just a rotation game. Just like we did back in chapter 1, finding stresses in different sections. Here, which we said a while ago, if I decide to rotate a section through some angle for theta, I rotate around Moore's circle by some angle 2 theta, and I can pick combinations of stress and of normal and shear stress off of the plot. All right. Cool. So this is great for ductile materials. The trick, though, is moving to stuff that's brittle, because actually stuff like glass, carbon fiber, all those kind of things, which are starting to become more and more widely used, you'll actually see failure criterion for them defined not by a stress, but actually by an elongation. The critical factor is no longer necessarily how much force you're applying, but how much the structure is distorting, how much it's changing in shape. So another way to look at this would be to use Moore's circle to determine maximum strains. So let's have a look at that. All right. Strains. I think it was around 20-ish. Nope. Okay, cool. So, all right. So this is going by the same kind of idea. You have some sort of little cube, and instead of saying, "Hey, we have a bunch of stresses poking at it," it's straining, it's deforming in some way. And we've already essentially gone through the derivations for this, because, well, if you remember back to when we originally started talking about stress transformations, we said, hey, what if I have some element and there's some and I have like some regular coordinate system, y and x, and some like angled coordinate system that's like y prime and x prime, and what's my sigma x prime, my sigma y prime, and all that jazz. Remember all that fun stuff? All right. Well, what's the relationship between stress and strain? How are they related?
Linear.
Linearly, in the region that we care about anyhow. Yes. What is the linear factor that relates them? Yes, some modulus of elasticity, some stiffness, be it a shear stiffness or a longitudinal stiffness or whatever, some Young's modulus or some shear modulus or whatever. So really, we can think about stress and strain in the same kind of way. Because really, if I just did some substitutions here, I could say, well, epsilon x prime times the elastic modulus is the same thing, right? More or less. So instead of boring you with another derivation, it suffices to say that it is more or less the same, let's call it the same thing. Oh, I did that. Okay. And you get something that looks like this. Two. And so let's call it and similarly in the y and gamma xy directions. But just to explain what I got here, so this would be like your longitudinal strain, your lateral strain, epsilon x, epsilon y, the rotation of whatever section that you're on. So we see our two thetas coming back, x. So that's going to act the same way as our Mohr circle for stress. Our gamma xy, so that's like a shear. So that's like a shear stress. Oh, missed a 2 there. And I'm just call and this looks pretty much identical to the stress equations that we had.
What's the symbol after the first?
It's a x prime, epsilon x prime. So like it's the normal strain in the x prime direction, same way that we had stress in the x prime direction. And if you boil all this down, you can say, hey, look, I do my trig substitutions and boils down to the equation of a circle again. Hey, isn't that awesome? And you can use your geometry to get some of the same expressions for like the average point as well as the radius. Oh, sorry, that's over 2. Cool. So strain, it's awesome. And through the math, it turns out that instead of your y-axis being just shear strain, it ends up being shear strain over 2, and that's why That's over 4. Yeah. That's what that's what that's about. All right. And the same way, I think I also gave an expression for expression two theta, yeah, an expression for finding the called the angle to the principal planes, and it's pretty much the same as before. The shear strain divided by the difference between the normal, between the normal strain, the lateral, in the longitudinal direction, and the lateral direction. So these should all look pretty familiar, right? Sweet. All right. So if, like, we're in the situation that I described, where we have a material whose failure criterion is built not on stress but on strain, then we can apply it in some sort of way like this. So we know these equations from before, right? That's just Hooke's law in 2D. This is, again, we're assuming plane stress because I don't like to solve cubics by hand. So based on some stresses, so say like you have some material, we've talked about how to find all these stresses via what you call looking at bending stress, torsion, normal, which call normal stress caused by axial loads, shear stress caused by transverse loads. We've talked about how to find all of these things. So hint, expect all those chapters to show up whenever we start like solving problems here, or if you ever want to solve problems with this. We can find all those stresses and give, as well as take the material properties of whatever material that we're playing around with. We can plug them into these equations for plane stress and plane strain. Remember, nu is your Poisson's ratio. This it should be about 0.3. It's a material property. So you can find it in the same table as you'd find the elastic moduli. Yep. Each material has its own one. Okay, so you can plug all these stresses into these plane strain equations, and then you can play the exact same Moore circles games that we just did, right? If I know what these three values are for a given state of stress, I can draw my axes. So I have my epsilon axis, so like my normal strain axis. I have my shear over 2 axis, shear strain over 2 axis. And I can say, okay, center, which call center point. I'm so used to drawing sigmas. It's just just an epsilon average. Okay, get that. Find a radius by the same sort of logic. I can start drawing. I can start drawing circles. Now, if this is like my epsilon 1, 2 circle, you could also find like an epsilon 2, 3 circle, epsilon 3, 1 circle, all by the same sort of logic. Just remember, I'm actually missing one of the plane stress equations here. Is there strain in the z direction? Why? So there's no stress in the z. but does Poisson's ratio have any sort of bearing on that, on the strain in the z direction? Possibly. So what does Poisson's ratio do? What is it a measure of? What is it? Right. Or in a more general sense, you could say that Poisson's ratio is how much the material deforms in a perpendicular direction due to how much the material is going to deform in this direction due to a stress in a perpendicular direction. And there are actually two perpendicular directions here, right? There's one that's going out of plane and one that's in plane. And if you have an isotropic material, one whose properties don't depend on direction, like we've been assuming here for the past 13 weeks or so, then Poisson's ratio is going to be the same when looking at the effect. This is like an epsilon z, it's an epsilon y, is a sigma x. This sigma x is going to cause the same amount of, it's going to correspond to an amount of strain in these two perpendicular directions by the same Poisson's ratio. So like I could say mu equals epsilon z over epsilon x. And I could also say, by the same token, mu equals epsilon y over epsilon x. Because you have an isotropic material, both those are true for a stress in the longitudinal direction. We cool with that?
What do you use for theta?
Theta? What do you mean?
Because, or I guess actually, do you need it? Well, when you do the epsilon x prime one from the last slide that you did, yeah, it's like cosine theta.
Yeah. So remember when we did the same sort of a game for stress transformations, we used some trig substitutions and said we can actually make all those thetas go away. So, and once you do that, it pretty much turns into the equation for a circle, and that's where more circle comes from. Yeah.
So they will go away.
Yeah, it's the exact same derivation. You just get an extra 1/2 attached to the shear stress, attached to the shear strain term. That's the only difference between the two. All right, cool. All right, and I believe that you guys have an equation from back in February that talked about how let's call that related an epsilon z to all these. But really, if you look at these expressions here, you have some contribution to the strain from the stress that's going in the same direction, and then you have some contribution from the stresses in the other two directions, right? So for epsilon z, in a general sense, I could write something like oh, come on. There you go. So for sigma z, in a general sense, I could write something like this. But sigma z is 0. And I'm left with something like that. Oh, because I dropped it. Yeah. And that's based on all that stuff, you could start to draw a generalized Moore circle because there's no shear strain in the tau xz or yz directions. All right, cool. So that's strain. So that's strain transformations in a nutshell. Cool. Just some terminology. Same way that you have principal stresses, you have principal strains too. So the normal strains are not associated with shears that don't have any shear strain. So the strain, so that plane that has no shear stress on it also has no shear strain. Makes sense. So principal strains associated with principal stresses. Usually your largest normal strains, they will be your largest normal strains, period. And that's, like as I said before, is of interest for the failure of brittle materials. This is called sometimes that can be your failure criterion. And that's, I think, where I'm going to pause for today. We'll talk about strain a little bit next week and how we can measure it, because we can't really directly measure stress. We can kind of directly measure strain. So because of that, we can kind of parlay our way into determining the stress on an arbitrary object in real time, which is awesome for doing materials tests and stuff like that. But that's all I got for today. Any questions?
What does gamma stand for?
Gamma is shear strain. Yep. Well, it's almost the same thing.
And that's the one that looks like a V on here.
That, yeah, yeah. That and that are the same thing. That. All right. Thanks for stopping by. I promise